Hey guys, this is going to be your lab over Bragg's Diffraction. So what we're going to do in this lab, or what the ultimate goal is we're going to have a styrofoam cube which is going to be embedded, which is going to have little metal balls embedded in it. And we want to find out what the lattice spacing, or what the spacing between those balls within different planes are going to be. Okay, and this is analogous to what Bragg did with his X-ray diffraction and finding the crystal and lattice spacing for different materials. So we're going to be using microwaves in our lab because these balls that are embedded within this styrofoam are going to have a lattice spacing that's on the same order of magnitude as the wavelength of microwaves, whereas X-rays have a very short wavelength, and so they are going to diffract off of the atoms within an actual crystal structure. So typically this is done with X-rays. In this lab we're using microwaves because they are safer and because it's easier to demonstrate using this ball with these, or this cube with these metal balls embedded within it. Okay, so before we talk about Bragg's diffraction and how we're going to use it to find lattice spacing, let's define a few things that within solid state physics. So anytime we have a lattice structure, we can define various planes within that structure using what's called Miller indices. Okay, and for a simple cubic structure like what we're going to be using, you can think of these Miller indices as being like an x and y and z coordinate that define the plane that we're talking about. So the first plane that we want to talk about is the 1, 0, 0 plane. And that plane is defined as this plane here, this horizontal plane. So if we connect all of these horizontal atoms together, the plane that connects those is going to be the 1, 0, 0 plane. Okay. And if we want to find the interatomic, or the interplanar spacing now of the 1, 0, 0 plane, it would just be the space between the two parallel planes, or the two planes that are next to each other. So this would be our, what we call the D100 spacing, our interplanar spacing for the 100 plane. Okay, another plane that we're going to be looking at in this lab is the 110 plane, and that would be defined by this plane here. So you can think of it as being up 1 over 1 within our cubic lattice. So this is the 110 plane. And so the neighboring plane would be this one here, right? And so the interplanar spacing between those two planes would be this spacing here. This is our D110 spacing. All right, and the final plane that we want to look at is going to be this one, right? That we define as the 120, right? We're going up 1 over 2. All right, so this spacing here now is the D120 interplanar spacing that we're going to be determining. Okay, so we have all of these planes that we can define using all of these indices, and of course these are not the only planes that we can define within our cubic lattice. These are just the ones that we're looking at in this lab. You can see that we're ignoring the z-axis, so all of these are on a 2D plane, right? Because this is 0 in this last one. So we're only looking at kind of a 2D plane and determining the lattice, or the interplanar spacing in that 2D plane among these different other planes. The equation, a general equation that relates all of these different atomic spacings to these Miller indices is the following. So if we want just a general DHKL, where HKL are the Miller indices that denote the plane that we're looking at, is going to be equal to A, which is what we call the lattice constant, which is what we're going to be trying to find, right? Square root of h squared plus k squared plus l squared. Okay, and this is only true for the case of a cubic lattice. So if we're looking at any other kind of lattice, like a hexagonal lattice, right, this would not be the case. But because we have a simple cubic, this is what this equation looks like. All right, and A is just a constant value that is unique to whatever crystal lattice that we're looking at. So whatever material we're looking at will have a different lattice constant A, depending on what the spacing between these planes is. Let's go ahead and look at what happens if we plug in 1, 0, 0 for this HKL value here. So we're going to look at this lattice spacing between the 1, 0, 0 planes and see how does that relate to this constant value A. All right, so we're looking at D1, 0, 0, which is going to be equal to A divided by the square root of 1 squared plus 0 squared plus 0 squared, which of course is just going to be equal to A. All right, so for the case of a simple cubic lattice, our lattice constant A is going to be equal to the D11 or the D100 interplanar spacing. This is only true, of course, for a simple cubic lattice. And this D100 spacing happens to also be what's called the nearest neighbor spacing. So if I look at any one atom, right, the spacing to its next nearest neighbor is going to, of course, be the ones that are on either side of it. Definitely not this one, right? This is the 1, 1, 0 plane, so that is not the nearest neighbor. It's this one or that one. And you can see that that nearest neighbor spacing is the same as D100 interplanar spacing, which is the same as A, right? So for a simple cubic lattice, the nearest neighbor distance is the same as the lattice constant A. All right, so that's just a few things to keep in mind as we go forward in this lab. So how are we going to go about experimentally determining all of these interplanar spacings? And then from those interplanar spacings, then how are we going to determine the lattice constant A? Well, that's where Bragg diffraction comes in. And so Bragg figured out we have this condition where if we have an incoming, in his case X-ray, in our case microwave, right? If we have an incoming ray, it's going to strike one of our atoms within our crystal lattice, and it's going to reflect at an angle equal to whatever its angle of incidence was. So if we're looking at the 1, 0, 0 plane, right, this is our angle of incidence with respect to that plane, and then this would be our angle of reflection, and those two angles have to be equal. Now, it's not going to only bounce off of that one, right? Another one might come in and bounce off this one right here. And then, of course, it's going to be reflected at an angle theta equal to its angle of incidence. So all of these thetas are equal to each other, right? And so after these two waves come in, right, they're going to be in phase, but after they leave, they're going to be out of phase unless a certain condition called Bragg's condition is met, right? And they're going to be out of phase because of the path difference that this reflected ray takes versus this other one incoming here. All right, so the space, so the difference in distance that this takes versus this is going to be this distance here plus this distance here, right? Because this and this are the same, this and this are the same. So this one, this second ray travels this distance plus that distance further than this one travels, right? And so if we want constructive interference, this difference in path has to be equal to some integer of the wavelength, right? If this has some integer of a wavelength, then these two outgoing waves are still going to be in phase with each other, right? Because anytime that we reflect, or anytime that we change the phase of a wave by any integer of its wavelength, it's going to just be the same wave over again, right? It essentially does nothing to the wave. And so if this path difference is equal to an integer of the wavelength, then these two outgoing waves are going to interact constructively. And this is what's known as Bragg's condition. And so we need to find a way of writing this path difference down in terms of this interplanar spacing between the 1, 0, 0 plane, right? That's what this distance is here, D 1, 0, 0 in this case. And so using these angles theta, the incident angle theta, and this distance d, you can determine using the geometry that this distance here is d sine theta, and then this one over here is also d sine theta. And so if we add those two together, we get 2d sine theta, which is the total path length difference between our two waves that are going to be interacting with each other. That has to be equal to an integer, so n times the wavelength. And this would be, in this case, we're looking at the 1, 0, 0 plane, so this would be 1, 0, 0, D1, 0, 0. We can do this for all of the other planes in the exact same way. So if we want to write a more general equation now, we can, instead of writing D1, 0, 0, we can write 2D HKL sine of theta has to be equal to n lambda if these two waves are interacting constructively. So this is only true, again, when these two waves are interacting constructively. So if we can determine at what angle these two waves interact constructively and plug that angle into here, we can then calculate the interatomic spacing or interplanar spacing for the planes that we're looking at. So how are we going to know whether these are interacting constructively or destructively? Well, we're going to have a detector over here, right? Some detector that's going to be taking in these outgoing waves or these reflected waves, all right? And they're going to convert the signal into a voltage. And so when this voltage that it's converting is at the highest, that means we have a constructive interference, and that means we can then use this equation. So at any other point other than when there's a maximum amount of constructive interference, we'll get a small voltage signal because these waves are going to be interacting and canceling each other out. Right? So whenever they have the most amount of constructive interference where this Bragg's condition is met, then we'll have a maximum signal that we're going to see over here on our voltmeter. Okay, and then so at that maximum voltage signal, we'll record this incident theta, and then use that theta to then calculate what our interatomic spacing is. Okay, and then so when we do this for the various planes, we'll have a value for D100, we'll have a value for D120, we'll have our value for D110, right? And so how are we going to use all of these interatomic spacings then to then calculate A? Well, that's where this equation comes in, right? So we're going to make a graph. And then on our Y, we're going to have our D, HKL values. And then on our X, we're going to have this 1 over the square root of H squared plus K squared plus L squared. Right? And so if we're linearizing this equation, right? So where DHKL is our Y, where this 1 over the square root of H squared plus K squared plus L squared is our X, which leaves only A as our slope. So we'll get some line here, like so, and this line for each value of this 1 over this root of H squared plus K squared plus L squared, for each one of those values we'll have our experimental value for the interplanar spacing that we'll graph. And then we'll draw a line of best fit, and from that slope of that line, we'll be able to determine A, our lattice constant, which of course is the same as our nearest neighbor spacing, and we should also check to make sure that which is the same as this D100 spacing for our cubic lattice. Okay. So that about covers the theory in this lab. What we're going to show next is how do you go, we're just going to demonstrate this process of shooting microwaves into our cubic lattice, receiving the outgoing waves, and then from the signal of our receiver here, we can then determine where these waves, at what angle these waves are interacting constructively, and then from that we can calculate these interatomic spacings. Okay, so that is what we will see next. All right, and here we are. This is the full setup for Bragg Diffraction. You can see over here we have our transmitter. So this is what's sending in the microwaves into our cubic lattice, in this case just styrofoam with these metal balls embedded. These metal balls are embedded all the way throughout the center of this ball. And then any reflected beams are then picked up by our receiver here. Okay, this receiver is then hooked up to a multimeter. So this receiver will take the incoming microwaves, convert it into a current and a voltage, which we then read out on our multimeter. Okay, and we can do a number of things. So if you look at the top of the cube here, you can see that the different interplanar, or the different planes are marked for us. And if we want to then find the if we want to then begin taking data for each plane, we can set our incident angle by looking underneath. So underneath here, there are these different marks that are in line with the different planes. So we have a 100 mark, we have our 120, and our 110. So those lines here are in line with the lines that are going across the top of this cube here. So it's a way of letting us know, or a way of us tracking the incident angle, or the incident angle that the transmitted waves are coming into contact with, whichever plane that we're wanting to measure. So the first data point that we need to take is at 20 degrees. All right, so what we're going to do is we're going to come down here and we're going to turn this goniometer. We're going to turn this so that that 100 mark is at 20 degrees from 180. So we're now at 160. All right. All right. So now this beam is now incident with 20 degrees with this 100 plane. All right, and now we want to pick up the reflected beam that's going to be reflected off of this plane. And to get that, we need to then turn our transmitter, but we can't, our receiver. But we can't just turn our receiver another 20 degrees, because if we do that, let's see what happens. If we just turn this 20 degrees, you'll see that this is now just 0 degrees with this. So these are in line with each other. So we need to turn this an additional 20 degrees because the angle of incidence is equal to the angle of reflection. So for this one, we need to actually turn it 40 degrees. So anytime that we change our incident angle to catch the reflected angle, we need to rotate this twice as far. All right, so for 20 degrees for the 100 plane, we would then record this intensity on our multimeter. Our next one would be 25 degrees. So again, we just come down here, make sure this line for the 100 plane is rotated by 5 degrees, which means we then rotate our receiver 10 degrees more, like so. So now this is 25 degrees to the 100 plane and 25 degrees to our receiver. And then we would again record our voltage. And we would repeat this until we get all the way to 70 degrees. And within that data, you should see, for the 100 peak at least, you'll see 2 peaks. And then we want to go back through this and take a higher resolution. So instead of going up by 5 degrees, you're going to look at around where your peak is. And then around that peak, you'll change the angle by 1 degree. So we can narrow in on where that peak is going to be. And wherever this is the highest, that's where we have constructive interference, and then that'll tell us what the angle that we need to use in order to plug into the Bragg's condition. Because remember, Bragg's condition is only true whenever we have constructive interference. Okay, so that would be for the 100. We would then repeat this for the other planes. So we just put everything back. Right? And so instead of now looking at the 100 plane here, we would make sure that our incident angles are taken with respect to the 120 for this one or the 110 for that one. So everything is exactly the same, except when we're doing the 120, we would rotate this line 20 degrees versus the other line, right? So now that plane is 20 degrees incident to our incoming beam. This, we would still rotate the same, so this would go 40 degrees, like so. And then we would just record our voltages in the same way. All right, that about covers everything that you would have done in this lab. Hopefully that makes sense, and we will see you next time.